Hi, I'm Paul Kyogan from GK Tuition, and in this video I want to talk to you about complex numbers. Now the question I've chosen to go through here is 2018 Paper 1 Question 4 Part A. In this question we're asked to prove by induction that cos theta plus I sine theta to the power of n is equal to cos n theta plus I sine n theta. In other words, prove de Moivre's theorem. Now the first few steps of this are relatively straightforward. In any induction question, the first thing you do is you prove it's true for n equals 1 or whatever value you're trying to prove it for. Now in this case, it's indicated that I want to prove it for all positive integers, so I'm going to prove it for the first one, which is n equals 1. That just means you take your original line, you sub in 1 instead of n, and you sub in 1 instead of n. When you do that, you end up with the same on the left and the right, so you can conclude it's true for n equals 1. Your second step is that you're going to make an assumption. You're going to assume that it's true for n equals k. In other words, you're just going to rewrite the question, except instead of an n, you're going to put in a k. We can work off the assumption for the rest of the question that this is true. And I've highlighted it there because it's impossible for us to finish this question without going back to our assumption. So in induction, always highlight your assumption. Now the difficult step is going to be step 3, and I've just started it off here. For step 3, I'm just going to consider n equals k plus 1. I need to prove that this is true. On the left hand side, all I've done is subbed in k plus 1. On the right, I've subbed in a k plus 1 and a k plus 1. Now I need to try and prove this. So I think maybe make sure you've got that down and try and do it yourself. If you can't figure it out, we'll do it on the next slide. Okay, so we've realized that what we need to prove is that cos theta plus I sine theta to the power of k plus 1 is equal to cos k plus 1 theta plus I sine k plus 1 theta. Now, in this question, what we're going to do is we're going to completely ignore the right-hand side. We're just going to take the left-hand side and try and turn it into the right-hand side. So from here on out, I'm only taking the left-hand side. On the left-hand side, my immediate problem is the k plus 1, is the two powers added together. Your first rule of powers is that a to the power of p plus q is equal to a to the power of p multiplied by a to the power of q. So with that in mind, I can take this to the power of k plus 1 is the same as this to the power of k times this to the power of 1. Now you can simplify the first bracket here by cos theta plus I sine theta to the power of k was the left-hand side of your assumption. In part 2, we highlighted that, and we said that this to the power of k is the same as cos k theta plus I sine k theta. Now you have two brackets, and it's just plain algebra. You're just going to multiply it out. The first thing in the first bracket multiplied by the second bracket. The second thing in the first bracket multiplied by the second bracket. When you multiply it out, you have no like terms. So when you multiply it out, you end up with this. Cos k theta plus I cos k theta sine theta plus I sine k theta cos theta plus I squared sine k theta sine theta. Now, in any awkward complex number proof, you always group your real terms, group your imaginary terms. So when we're on this line, you need to recognize that my real terms, the first term here is real because there's no I in it, and the last term will also be real because I squared will become a minus 1. So in the next line, all I've done is I've grouped my two real terms, cos k theta, and this becomes minus sine k theta sine theta. And then you group your two imaginary terms, where the two that were in the middle previously. It's I cos k theta sine theta plus I sine k theta cos theta. It's the next line that's really obscure, so I've added in a bit here. When I have this cos k theta minus sine k theta sine theta, I want you to look at page 14 in your log tables. On page 14 in your log tables, there's a formula for cos A plus B. Cos A plus B is equal to cos A cos B minus sine A sine B. I want you to realize that we have the exact same thing here, except that instead of an A, we have a k theta, instead of a B, we have a theta. This is the same. This is cos k theta minus sine k theta sine theta. That's the same as if I have cos A cos B minus sine A sine B. In other words, these two terms, based on that rule on page 14 in your log tables, just become the cos of A plus B, or in this case, the cos of k theta plus theta. So those two terms just become cos k theta plus theta. Once you've got that, the other two terms are very similar. If you look at the same page in your log tables, the formula for sine A plus B. The formula for sine A plus B is cos A sine B plus sine A cos B. That's exactly what we have. We have cos k theta sine theta plus sine k theta cos theta. Instead of an A, we have k theta. Instead of a B, we have theta. Now just be aware, you can just factorize out your I. There's an I in both of these terms, so you can just factorize out your I. So more or less we can ignore just put it in front and ignore the I. So that's exactly what I've done. I've factorized out my I, and then cos k theta sine theta plus sine k theta cos theta just becomes sine k theta plus theta. Now, always, I just want to have it exactly the same. I want to rewrite it exactly the same as the right-hand side was. I was trying to prove that this, the left-hand side, is equal to cos k plus 1 times theta plus I sine k plus 1 times theta. So on this line, all I've done now is factorized out my theta. If you take k theta plus theta and you factorize out theta, you're left with cos k plus 1 times theta plus I sine k plus 1 times theta. And that's my left-hand side. The final line now, I've reintroduced the right-hand side. So that the left-hand side now is equal to the right-hand side. So I can tick that and say that it's true for n equals k plus 1. Then my final step is I'm just going to have to make a statement. I'm just going to have to make my statement to prove that it's true. So the last part of this question is just as important. To conclude your induction, you always finish it off like this. So to conclude it, I'm going to say, right, well, the proposition is true for n equals k plus 1 if it is true for n equals k. In other words, in part 3, I proved it was true for this based on the assumption that from part 2, it was true for n equals k. It's true for any number if it's true for the previous number. But in the first part of the question, I worked out that it is true for n equals 1. If it's true for that number, I know that it has to be true for the next one. So if it's true for n equals 1, therefore it must be true for n equals 2. And therefore, if it's true for 2, it must be true for 3. If it's true for 3, it must be true for 4, and so on. I could do that forever. Basically, it's true for all the natural numbers, or n is an element of the natural numbers. You could even rewrite it, the wording on the question was for all positive numbers, so you could rewrite it like that either. But in your induction, make sure you always do your last step to conclude. In the second part of this question, we're asked to hence or otherwise find this number to the power 3. Okay? The otherwise they're referring to here is you can actually just multiply this by itself 3 times. However, you're probably better off if you use the Moivre's theorem. The hence in this case, since we're just after proving the Moivre's theorem, hence means use the Moivre's theorem to get this to the power 3. Now, in order to use the Moivre's theorem, the first thing we need to do is get this in polar form. If you want to get a complex number in polar form, you need to find 2 things. The first thing you need to find is your modulus. The second thing you need to find is your argument. So as you can see, I've already gone through how to find the modulus. The modulus, your formula for the modulus is just the square root of a squared plus b squared, where a is the number on its own and b is the number in front of I. In this case, my modulus is the square root of minus a half squared plus root 3 over 2 squared. If you plug that into your calculator, your modulus is 1. The second thing we need to find is the argument. And in order to find the argument, we're going to draw an argand diagram, where the horizontal line is the real axis and the vertical line is the imaginary axis. And we're going to plot our point. Our point here is the real is minus a half, so let's say it's roughly out here, and the imaginary number is root 3 over 2. Okay, so if I was to plot this point, it's minus a half plus root 3 over 2 would roughly be there. In order to find the argument, we need to find the angle that this complex number makes with the x-axis. Okay, so the first thing you're going to do is form a right angle triangle between the origin, the complex number, and the real axis, the horizontal line. And I want to find this angle, the angle A. Based on the diagram I've drawn, I know that the distance from there to there is root 3 over 2. And I know that the distance from here to here is a half. Now if you think back to junior cert trigonometry, this is a right angle triangle. You know the opposite and you know the adjacent, which means you can use tan in order to find the angle, because you know that the tan of an angle is always the opposite over the adjacent. So in this case, I could say the tan of this angle is root 3 over 2 divided by the adjacent, which is a half. Now if you simplify that down, that's actually just the square root of 3. So you can say that the tan of A is equal to the square root of 3. If tan A equals square root of 3, to get A on its own, it's just tan inverse of root 3. And then you can leave your answer here in degrees or you can leave it in radians. I'm going to go with radians. So if you read this off your log tables, you use your calculator, tan inverse of root 3 works out as pi over 3. So now pi over 3 is the same as 60 degrees. So if you're using 60 degrees there, that's fine. But A is not the argument. I'm looking for the argument, which is the angle that the complex number makes with the positive sense of the x-axis. You know, the positive sense of the x-axis starts over here and goes in this direction. That's the angle I'm looking for. That's what we call it theta, and that's our argument. So I'm looking for this angle. And we're just after working out that the angle here is 60 degrees, or in other words, pi over 3. So if you think about it, it's probably easier to think of it in degrees. If that was 60 degrees, you know the whole thing is 180. So 180 minus 60 would mean that that angle is 120 degrees. If we're talking about radians, remember in radians, 180 degrees is the same as pi. Which means if I know the distance from there to there is pi, and I know that this one here is pi over 3, well then in order to work out what this region would be, it would be pi minus pi over 3. Which means the argument in this case just works out as 2 pi divided by 3. So now we've worked out our modulus, we've worked out our argument. Once you know the modulus and the argument, you can write this complex number in polar form. So we were given a complex number in rectangular form, and we will convert it from rectangular form to polar form. So we were given minus a half plus root 3 over 2i, and I know that that is the same as 1 times the cos of 2 pi over 3 plus I times the sine of 2 pi over 3. So all I've done there, my modulus is 1, my argument is 2 pi over 3. The question was to get this complex number to the power of 3. Which means that I need to get this complex number to the power of 3. Once you have a complex number in polar form and you're getting it to a power, this is where you can apply your de Moivre's theorem. So if you just look up at what we did in part A, we're just going to apply that rule. If I apply de Moivre's theorem here, it becomes my modulus to the power of 3. So it becomes 1 to the power of 3. And instead of actually multiplying this by itself 3 times, all you have to do is multiply the angle by the power. So all I need to do is multiply 2 pi over 3 by 3 and 2 pi over 3 by 3. If you multiply 2 pi over 3 multiplied by 3, the 3's just cancel and you're just left with 2 pi. Which means that this actually just becomes the cos of 2 pi plus I times the sine of 2 pi. So all I've done at that stage is I've just applied my de Moivre's theorem. So the modulus to the power of 3, then you multiply the angle by the power. 2 pi over 3 by 3 gives me 2 pi. Now always work off the assumption that you want to leave your answer in rectangular form. Or in other words, in this form that we were given originally. 1 cubed is just 1, so I don't need to worry too much about that. The cos of 2 pi, now to get that, make sure you have your calculator in radians, or else you can just read it off page 13 in your log tables. The cos of 2 pi is equal to 1. And the sine of 2 pi is equal to 0. So that means I actually just get 1 times 1 plus 0i, which if I multiply it out, my final answer is just 1. Now I hope this video made sense. If there's anything you're unsure of there, then just ask me to clarify it, send me an email or let me know in class and I'll try and explain it differently for you.